This is Veritasium's ball beaker problem. If you don't know what the problem is, basically we're just asking which way does this kind of balance rotate. So, same distance, so in terms of torque, right, we're just looking at kind of which one is kind of heavier, right? If you had a same beaker with the same amount of water, but I have two balls added to it that are the same density, or it's not the same density, same volume. This one is less dense than water, so it floats, which is why there's actually a string keeping it tethered to the bottom like so, to stop it from just floating all the way up. This ball is more dense than water, so there's a string that kind of keeps it up instead of sinking. So, density of the mass kind of impacts like whether it floats or sinks. And if you're in AP Physics 1, you'll learn all about that towards the end of the year. But that's really all you kind of have to know. And we just got to figure out which way does it rotate. Now, I'm going to just walk through it and we'll figure out if there's an answer. So, when we're trying to figure this out, we got to see, well, which one is kind of exerting a bigger force on the part of the scale, right? Which one is kind of heavier, kind of pushing down on the scale more. So, let's say initially they're like kind of, I keep it still and then I let go and it starts rotating. Well, the instant that it kind of starts rotating, the force up on the beaker, right? So the surface is going to exert a force on the beaker. Beaker is going to push down back, and that's really what we're trying to finding is, hey, which force is bigger? And what we can do is we can make an FBD and kind of figure out which one is pushing down more. So basically, let's first start with FBDs of the ball. And the reason we're going to start with FBDs on the ball to kind of see what forces there are is because if we have this ball right here, there's obviously going to be force gravity, all right? Usually you should write FG. I'm just going to write MG. Sometimes in college you'll see it like that or other places. So there's obviously going to be a weight force, but it's balanced, so it's not accelerating, so there's got to be no net force. There's obviously going to be the buoyant force. Now the buoyant force is going to be bigger than your FG. So that's why we have the string, right? The string is what keeps it down instead of having it float all the way up to the top. There's also going to be a buoyant force. So what we can, or not a buoyant force, I'm so sorry. This is a tension force pulling down on the thing. So let's now, if we were to draw an FBD of the beaker, I'm going to ignore the weight of the beaker and the weight of the water inside of the beaker because they're the same, so really that shouldn't have any effect on our final answer. But in terms of the beaker, the water in the beaker, right, if there's a buoyant force on the ball, it's pretty crazy. The ball is going to kind of exert like an equal and opposite kind of buoyant force, not really a buoyant force, but a force downwards that is equal to the buoyant force. And that's kind of crazy. All right, so now there's going to be a buoyant force of a, there's going to be, sorry, what am I saying? Wait, there's going to be the buoyant force downwards, which is going, and we're going to solve for all these values. I'm just drawing an FBD. But there's also going to be the Ft down that is keeping the ball down, Newton's third law. It's going to be pulling up on the beaker. So the beaker actually has some of that equal and opposite. I'll draw it smaller just to make it more clear. But that equal and opposite force tension. So there's also got to be wait, but before I get to before I keep going, I want to kind of show you something. If we were to think about the net force right now, so for the ball, we know that FB, so the upward forces minus the downward forces, mg minus ft has to equal 0. And right here, the current net force is FB minus ft. Well, take a look. FB minus ft, if I add mg to both sides, we have FB minus ft equals mg. So this current downward force is equal to Fg, or sorry, yeah, mg, right? The mass of this ball times gravity. So or gravitational field strength. What I can do is I can just draw one now instead of those two forces. There are still those two forces acting on it, but I'm going to show that it's like, I'm going to pretend it's kind of only one force that is equal to mg, which is going to be less than force buoyant, right? Which is why it's a smaller arrow, because Ft is kind of taken away from there. So we know now, well, obviously, you know, in order for this beaker to not fall down, this is pushing back up. So we now know that this thing, by Newton's third law, right? This is a whole lot of Newton's third law. If this is a force up on the beaker, which is equal to mg, it's also pushing back down equal to the weight of the, well, not exactly equal to the weight, but it's going to be equal to the weight of everything else plus the weight of the beaker. It's pretty cool. So now what we're going to do is we're going to kind of do the same thing for this guy. And really what we can do is we can kind of draw this FBD for the ball. Big mg, because it's a little bit more massive, right? More dense, same volume, more mass. Mg, there's going to be some Ft upwards, but there's also going to be still, and you'll learn this with Archimedes' principle, there's actually still a buoyant force. By Archimedes' principle, there's actually a bit of a buoyant force that's going to also help keep this thing afloat. And the Ft is going to take care of the rest since it can't fully float. So now we just got to apply Newton's third law. On the beaker, right? On the beaker, it's going to be that equal and opposite force buoyant down. One thing to note is that these force buoyants are the same. And that might even start showing you what might the answer actually be, of which way it's going to go. But to kind of show you with like things that we know, like the masses and stuff, instead of force tension, because you can actually get the answer right now, but whatever. Fb, well, if you take a look, if we do Fb plus Ft is minus mg equals 0, we get that Fb is equal to mg minus Ft. What I can actually do is I can say, well, here, this buoyant force, these buoyant forces are the same, because they're the same volume, and they're displacing the same amount of water, and by Archimedes' principle, they'll have the same buoyant force. I can say Fb is equal to mg plus Ft, and I can actually set these, and I'll make this like T1, T2, I can actually set these equal. And I can say mg, I'm going to kind of do this right here, mg plus, and I'll maybe do it like this, plus Ft1, right, is equal to mg plus Ft2. Okay, now what I can do is I know this is going to be equal to mg minus Ft2, right? Right, oh my god. This Fb is really just equal to mg minus Ft2. But take a look. This is like the same thing as this, right? I can just substitute in little mg, right? The little mass. And it's kind of crazy because these aren't connected. I'm not saying that this is causing a force on this. I'm just showing mathematically speaking, this force would be equal to in size mg plus Ft2, and that, or Ft1 really, and that would kind of give us our answer. This is pushing down with like that force of mg, not completely, but there's going to be mg, but this is going to be mg plus Ft. There's more force being pushed down. It's going to be kind of heavier on this side. It's going to rotate this way. Hopefully, and you can watch this video on Veritasium channel. This is actually the result. Thank you for watching. And I'll catch you later.